Thank you.
What, Brad? Why?
No, just
Oh,
yeah.
so I'm so tired.
Yeah, if anyone else has assignments to hand in, throw them up here.
Do a little each day, not all day.
Yeah.
Yeah. Oh.
I'll walk up Glen Mountain. I'll walk up Glen Mountain. I'm happy.
I plan to run to said we can steer.
Yeah. Okay. Yeah. Yeah, there you go. Yeah.
Thank you. Great, thank you. Oh, what happened to the projector?
Oh, yeah,
Then
yeah,
you run there.
yeah, yeah.
Run to there.
It's about 2 miles to one lap.
Yeah.
If you're walking, it's twice as much.
Yeah, but because long time not doing
Yeah, yeah, yeah.
so I need to practice longer
Okay,
longer and longer.
it's 11:30. So it's time for me to get started. I'm not sure why this projector is still not. You see, I'm not sure why this projector is still warming up. Anyways, so I just want to mention a couple things before while this projector is warming up. The first is, okay, if folks could listen up, that'd be great. So the first thing I want to mention before we get started is, again, that written assignment is due today. If you have it to hand in now, that would be great. If not, send it to me in email tonight. You can probably send it to me in email tomorrow morning. I'm not going to be marking it till tomorrow afternoon. And again, what is this with this projector? Why is it flashing off? PC on. What does that mean? Sorry, for some reason the projector is like right on the picture is off, flashing. Can I just need to find this thing on this side? Let's see if that works. That seems to be working. Okay. Okay, yeah, now it's starting up. Okay, anyways, so just to mention, yeah, the written assignments, please get them to me before tomorrow afternoon. I'll be marking them tomorrow afternoon. One of the things to mention is on Thursday and Friday this week, I will be in Kelowna for what's called a Flipped Classroom Conference. I'm just going to talk a little bit about that because it interests me. And I just want to talk a little bit about what, why I'm going to be out of town and what I'm going to be learning while I'm there. A normal classroom, right, this is the sort of the standard model of teaching is that, in class you have lectures, right? The teacher's up there like doing stuff at the board for most of the class. And then you've got homework that you do at home. Now there's some of us out there who feel like this is not the most efficient way to teach. I don't particularly like this. I definitely teach better when there's dialogue going on than when I'm just, lecturing in front of you. And what people who advocate the flipped classroom model have said is that lectures are much better accomplished through videos. Because oftentimes when I'm sitting up here up at the board doing examples for you folks, I'm not actually getting a lot of questions, I'm not actually getting a lot of feedback. So that might as well just be a video that you can watch in your own time. The advantage of videos is you can pause them and rewind and play over something again if you missed it. You can yeah, you can, there's lots of, you can go through it 3 or 4 times. You can fast forward through something if it's something you already understand. But the idea is that that the lectures would actually happen at home in videos. And in class, there's things like group work that happens, you know, individual work with feedback. Other sorts of activities. And the idea here is that the time in class, like people who advocate for the flipped classroom model say that the time that's in class should be used for interaction between the instructor and the students. The time that's happening in class should not be used for the instructor talking with the students listening. But there should always be dialogue going on during class time, because it's the only time you actually can have dialogue. Whereas at home, outside of class, you can have, lectures can happen very easily then, when you know, whenever, and students can choose when they want to watch the videos, that sort of thing. So it's something I'm looking at. I don't yet have the skills to make good quality video lectures, which is the reason I'm not doing it yet. This is one of the reasons I'm actually recording my lectures, is partly to help me figure out, you know, what makes for a good video, so I can sort of look at these sorts of things and see how they're doing. I might be able to reuse some of them later. But anyways, so this conference I'm going to on Thursday and Friday is talking about this. There's a bunch of sort of workshops on, you know, how to make good videos, a bunch of workshops on, you know, what can you do with it in class time if it's not spent lecturing, that sort of stuff. So that's where I'm going to be on Thursday and Friday. On Thursday, because of course we don't have this class on Friday, on Thursday I will have a substitute instructor, Stan Manu, is going to be here. I don't know if any of you had him before Calculus 1 or, okay, there are a couple folks. Anyway, so he'll be here on Thursday. He'll be covering his class for me. I'll be sending him a list of what he needs to cover. So yeah, so he'll have that. And I'm heading up to Kelowna tomorrow night, which is one of the reasons I said I'm not going to do marking until tomorrow afternoon, because I'm going to be marking on the bus up to Kelowna. That's because, you know, long bus rides, it's difficult for me to find stuff to occupy my time, and marking is one of the things I can do on a long bus ride. So anyways, so anyways, I'm going to be marking these assignments tomorrow evening, so probably if you get them to me tomorrow morning or early afternoon, I will still be able to mark them in time. And they won't be counted as late. So, the agenda for today's class, again, there's no muddies points for today's class, because the last class was the test. What we're going to be starting today's class, we're going to be starting Chapter 7. Chapter 7 deals with different techniques of integration, different ways of actually evaluating integrals. The substitution rule is the first and the most important one that we covered back in Chapter 5. But there's a whole bunch of other rules and techniques that you can use to evaluate integrals, which are going to come up throughout Chapter 7. We're going to do Section 7.1 today. I'll divide it into 3 parts. We're going to start Section 7.2 today. We won't finish Section 7.2. Hopefully we'll get through the first half of it, though. And then on Thursday's class, Stan will be covering the second half of 7.2 and Section 7.3. Here are the handouts for today's class. I've got 7.1 and 7.2 in the same handout to save paper. And then, yeah, again, as usual, at the end of class, there should be some time for group problems. Any questions about the agenda before I start into Section 7.1? Oh, by the way, I've got the tests marked. Hopefully you've all seen your grades online through WebAssign. I'll be handing them back just at the beginning of the break. So. Okay. Oh, not yet. Okay. So Section 7.1 that we're going into now is called integration by parts. It's sort of the next most important technique of integration after substitution, which we covered in Chapter 5. Now, how many people here have covered integration by parts before in a previous course? Is there anyone here who has learned it before but completely forgotten it? Okay. And who here has never seen these sorts of things before? I was guessing that was going to be what the class was. There actually seems to be a fair number who have seen it before. Anyways, when you're doing integration by parts, you have u's and dv's. The notation looks very similar to substitution. The main difference between the two is when you're doing substitution, you're sort of undoing the chain rule. The rules of integration by substitution is related to the chain rule. Integration by parts is related to the product rule. So integration by parts is sort of the opposite of the product rule. So what we're going to be talking about first just is how do we integrate by parts? How do we actually undo the product rule? So the idea is the product rule looks like this, right? What we want to do is we want to take this product rule for derivatives and turn it into a product rule for integrals. So it says the derivative of f of x g of x is f prime of x g of x plus f of x g prime of x, right? The derivative of the first times second plus the first times the derivative of the second. Well, if the derivative of this is this, then the integral of this is this. So one way of sort of writing out the opposite of the product rule is that f of x g of x, f of x times g of x, is the integral of f prime of x g of x plus, sorry, I'm doing this way, f of x g prime of x. dx. Right, that's one way of, right, that's just one way of writing sort of the product rule using integrals. Now here we have an integral of a sum, so we can split it up as a sum of integrals. So it's the integral of f prime of x g of x dx plus the integral of f of x g prime of x dx, which is that formula there. Now the key thing is there's two integrals in this formula. And what we really want is a formula which will allow you to evaluate one of those integrals. So what I do is I take one of them and I move it to the other side. So I'll get a formula that looks like the integral of f of x g prime of x dx is f of x g of x minus the integral of f prime of x g of x dx. Right, if I want to integrate something like this, I can do it by taking a product of two functions, then I'm going to have to subtract this other integral. And it's one of the annoying things about the product rule for integrals, about the rule of integration by parts, is that we're always going to be left with another integral that we will still have to integrate. It's just sort of like substitution. Substitution allows us to turn one integral into a simpler integral. Same thing will happen with integration by parts. We'll start it with this integral, and we'll get something that's already been integrated minus another integral. So again, this is the formula we get. I'm taking this product formula and rearranging it, and this is called the formula for integration by parts. Any questions about where this formula came from for now? Just to mention that some students like to know where this formula came from. Other people just memorize it and use it. It's up to you which one you want to do. If you're one of the people who likes deriving formulas and you know the product rule off by heart, you can go about deriving it the same way that I did. But if not, feel free to just memorize this. Ooh, that's weird. Anyways, I clearly made a typo here, and it turned into this symbol instead of this symbol. When I'm entering symbols on my computer, I enter them via the keyboard. The first symbol is the symbol INT for integral. The second one is the symbol in. So clearly I forgot a T when I was typing it in. I was doing this fairly late last night, so that's one of the reasons I'm making these sort of silly mistakes. Anyways, this is supposed to be like this. That formula is supposed to look like this: integral of u dv equals uv minus the integral of v du. The idea here is this is just sort of an abbreviated version of this formula. In this formula, I'm calling this f of x u, and g prime of x dx I'm calling dv. The idea is d something is the derivative of that thing times dx. right? That's what I mean when I say du. It's the derivative of u times dx. So if v is g of x, then dv is g prime of x dx. F of x times g of x is u times v. And here, this g of x is a v, and this f prime of x in the dx is a du. So this is just sort of an abbreviated version of that formula. This is oftentimes easier to memorize, so often when we're doing integration by parts problems, I'm usually going to be using this formula rather than this formula. Usually writing things in terms of u and v rather than f of x and g of x. So the idea here is that when we're doing integration by parts, what we're trying to do is we're trying to take the function we're trying to integrate, and we're trying to split it up into something which is a u and something which is a dv. Basically, the u is going to be some function, and the dv is going to be the derivative of some function. And what we're going to have to do is we're going to have to find what the derivative of u is and what the antiderivative of dv is. Right? This du is the derivative of the u we started with. This v here is the antiderivative of the dv we started with. So when we're doing integration by parts, one part we're taking the derivative of, the other part we're taking the antiderivative of. And one of the things that will come up later, which I'm going to mention, is it's going to be very important to know how to choose which part to be u and which part to be dv. Because if we choose them wrong, we'll end up having a very complicated derivative or a very complicated antiderivative. So our goal is always to make sure that this integral here is simpler than the one we started with. Because if we're finish this problem, we're still going to have to integrate this integral. And hopefully, even though this one was too hard to do without integration by parts, this one we will be able to do without integration by parts. That's the idea. So we want to make sure that this one is simpler than this one, which means we usually want to pick our u to be something which, when you take its derivative, it gets simpler. And you want to pick your dv to be something which, when you take its antiderivative, it also gets simpler. That's oftentimes a useful way of evaluating these sorts of integrals. Any questions about this u and dv notation before I move on to examples? Okay. So I've got two examples to do for now. One was a definite integral, the other one's an indefinite integral. One thing to mention is when we're doing indefinite integrals, again, indefinite integrals always have to have that plus c on the end. When we're doing indefinite integrals, we always wait to the last step before we add the plus c. Otherwise, you could end up having, you can add the plus c earlier if you want, but when we do it, it's going to make things more complicated. Whereas if we wait to the last step and then just tack it on at the end, it makes things simpler. So, yeah. So as long as you remember to tack on the plus c at the end, we don't have to tack on the plus c in between steps. So, example 1 here, we want to evaluate this integral here. The integral of theta cos theta d theta. So here we have, this is example 1. We have theta cos theta d theta. So the idea is we want to call part of this thing u and part of this dv. I have said here that u is theta, and dv is cos theta d theta. I've already told you this problem. Later I'll talk about how you would know that that was the u and that's the dv. Well, in order to use the formula for integration by parts, I need to figure out what du is. What's the derivative of theta? The derivative of theta is just 1. And it's going to be 1 d theta. Because a du will always have like a dx, and here the x is theta. If you want to use the antiderivative of cos theta, the antiderivative of cos theta is sine theta. And again, we don't need to put a plus c on here. Wait to the last step before we put any plus c's on. Otherwise, it's going to make things more complicated in the middle that you shouldn't have to do. So dv is cos theta d theta. V here is sine theta. So this thing will give you uv minus the integral of v du. That's what the formula for integration by parts says. Here uv is theta sine theta. The integral of v du is the integral of sine theta d theta. Now, this integral is simpler than the one we started with, right? Integral of sine theta d theta is simpler than the integral of theta cos theta d theta, right? And the reason this got simpler is because when we took the derivative of u and we took the derivative of theta, we just got a y, right? So that's what made this thing simpler. And here, when we took the antiderivative, it didn't get any more complicated. Cos theta and sine theta, same difficulty. So this is now a simpler integral than what we started with, and it's one we can evaluate. So the antiderivative of sine theta is negative cos theta. So it's theta sine theta plus cos theta. And now tack on the plus c in the last step. Again, you can't, there's nothing wrong with doing it earlier, but if you do it earlier, we'll have these thetas, there's plus c's inside brackets, and it'll make it more complicated than it needs to be. So this is what that integral is going to give you. And if you want to check, you can take the derivative of this. Take the derivative of this, do the derivative of this with the product rule, do the derivative of this guy, they will cancel each other. We term that cancel each other out, you'll be left with theta cos theta. Any questions about example 1? Okay. No, I'll move on to example 2. So example 2 is going to be an example of a definite integral. One thing to mention when you're doing integration by parts with the definite integral is the limits of integration are not going to change. When you do substitution with definite integrals, the limits of integration will change. When you do integration by parts, the limits of integration will always stay the same. The only thing is you have to put the limits of integration on this part as well as this part. So this part will put the limits of integration here and here. On this part, we'll draw a vertical bar and put the limits of integration above and below. So we're plugging the limits of integration into the u times v term, as well as putting them on the v du term. So here, example 2, we have the integral, oh, this is the other dead one. Look at that later. The integral from 1 to 2 of ln x dx. So the key thing here is, again, it's told you what the u and the v is. The u is ln x, and the v is the dv, is dx. So if u is ln x, we take the derivative of it, we'll have 1 over x. Right? The derivative of ln x is 1 over x. If dv is dx, we take the antiderivative of that. The antiderivative of dx, again, you can think about it as 1 dx, is x. So now if we write out this integral, we're going to have u times v, which will be ln x times x, minus the integral of v du. And the thing to mention is we need to put those limits of integration in. The limits of integration here were 1 and 2. So I put a 1 and 2 on this integral, but I also put a 1 and 2 on the ln x times x. Limits of integration need to go both here as well as here. And again, this part, there's no integral signs, so that's why we put the limits of integration on the vertical bar. Here there isn't an integral sign, which is why we put them in like that. So to finish things out, there's 2 things we need to do. First, we need to plug the limits of integration into here. When we do that, we'll get ln 2 times 2 minus ln 1 times 1. Right, that's what we get from that first thing. Minus, now x times 1 over x, that's just 1. So this is now really easy to integrate. Again, you always want to make sure that the new integral is easier to integrate than the original integral. 1 is a lot easier to integrate than ln x is. So ln 2 times 2, I'm just going to write as 2 ln 2. ln of 1 is 0, so ln of 1 times 1 is just 0. Integral of 1 is x. And that needs to go from 1 to 2. So here I'm going to take 2 ln 2. And for x, I'm going to take 2 minus 1. Plug in 2, plug in 1 and subtract. 2 minus 1 is just 1. So the final answer here is 2 ln2 minus 1. Any questions about example 2 here? Okay, so I'm going to move on to talking a little bit about how do we pick the U and how do we pick the dB. So we're going to see these ones are a little bit more complicated than ones we've seen so far, right? Here we just had theta cos theta. Here we just had ln x. So they're both pretty simple functions. Here we're going to have more complicated things like x cubed e to the 4x that we're going to have to integrate. We're still going to use the same strategy of integration by parts. And the key thing here is we're going to have to figure out how do we pick what U is, how do we pick what dB is. Is anyone here who has done this before? Can they tell me what the U and the dB are here? If no one can, that's okay. I was just curious if anyone knows that from previous courses. Yes?
Isn't it like some rule where you can there's like a letter system, like
There is.
or something like that?
Oh, I haven't learned that before. That's a good. Let me know. Do you remember what? Either of you remember what that letter system is?
It's Liate, logarithmic, inverse trigonometric, algebraic, trigonometric, and exponential.
Thank you. I have. Yeah, I have not actually learned this before, but this is.
99% of the time it
Yeah.
works.
I have a different way of remembering it, but this is also yes. Okay. So the idea is the order here. Whatever comes first in this order is what you call your U. So here, this x cubed is algebraic. It's like a polynomial. This is an exponential. So this is your U. This is your dB.
Yeah.
So the x cubed is U. The e to the 4 dx is the dB here. But thank you. No, I was going to say because I learned it differently than this, and I didn't even know that specific Liate works. Anyways, so I will mention that. I formulate it differently, but it basically says the same thing. So the guidelines I use for picking U and dB are these. So there's 3 situations in which integration by parts are useful, and each situation is a separate guideline. It turns out that technically speaking, there are more than these 3 situations. These are just the 3 that come up in the textbook. But for example, I don't have one that has both a logarithmic and inverse trigonometric. There aren't any in the textbook because those would be too hard. Or one that has an inverse trigonometric and a trigonometric. I only have 3 different combinations that actually occur in the textbook. So the first one is if we have a polynomial or any algebraic function, if we have like an x, if we have the square root of x, if we have a 1 over x, and we have an exponential function, something like e to the x, we'll always call the polynomial function u. And the reason for it is if you take the derivative of a polynomial function, it gets simpler. Take the derivative of x, you get 1. Take the derivative of x squared, you get 2x. Take the derivative of x cubed, you get 3x squared. So if you've got a polynomial function, you always want that to be your u, because your u is what you're taking the derivative of. Right? So you want that thing to get simpler. Again, this thing is the thing I'm taking the derivative of. And if you have a sinusoidal function, so like sin x or cos x, or an exponential function like e to the x, those don't get any more complicated when you integrate. That's the idea there. Second scenario is if you have a logarithmic or inverse trigonometric function, something like ln x or tan inverse of x. Those are things you can't integrate at all, or you can't take the antiderivative of at all. So you're never going to want to call those things dv. You're always going to want to call those things u. So it doesn't matter what it's with. If you have a logarithmic function times an exponential function, the logarithmic function is u, the exponential is dv. If you have a logarithmic times a trigonometric, logarithmic is u, trigonometric is dv. If you're trying to logarithmic function something that's really complicated, even like it's like x squared minus 2x plus 3 over x cubed minus 4, right? Like that's the logarithmic is still your u, that thing's your dv. And the reason is because we can't. Logarithmic is very difficult to integrate. So if you have a logarithmic or inverse trigonometric function and any other function, the logarithmic or inverse trigonometric function are your u. Again, those are sort of the 2 first things in the Liate. And the third scenario is if we have an exponential and a sinusoidal function, so e to the x times sine x, e to the x times cos x, or 2 to the x times sine x, or 2 to the x times cos x. It turns out it doesn't matter which one you call u and which one you call u dv. There's a certain special trick we need for dealing with those sorts of guys, which I'll bring up later. It requires integrating by parts twice and moving something to the other side of an equation. But this particular scenario says you call the trigonometric one u and the exponential one dv. That works well because the trigonometric one is easier to take the derivative of, exponential one's easier to integrate a little bit. So I'm just going to, so those are the 3 guidelines I give. Again, Liaid also works. I'm just going to write this on the board for those who want to use it that way. So logarithmic, inverse trig, algebraic trig, exponential, and the higher one is u, and the lower one is dv. That's the idea. So if you've got a product of 2 functions, whichever one is higher on that list, you call u, whichever one's lower on the list, you call dv. Or you look at these 3 guidelines. Again, it's definitely possible to get problems that don't fit into one of those 3 guidelines. All the ones I would give you on the test will fit into one of those 3 guidelines. So that's one, yeah. But this is a little bit more general for anyone who's going to take on like more calculus courses. That's probably better. Is that outside? I was like, trying to figure out what that sound was, but it's somewhere outside. Okay. Any questions about these guidelines before I go on to examples using them? Oh, you know what I was going to do, and I should have. I was distracted by this whole Liaid thing. I was going to show you an example of each guideline, just showing you what you would call u and what you would call dv. So if I had this, x cubed plus 1 times 3 to the x dx. In that situation, I have a polynomial function times an exponential function. So in here, I'm in the top scenario. So in guideline 1, I'd call this thing u, and I'd call this thing dv. This is an example of guideline 1, the first one. There's a polynomial function times an exponential function. For example, the second one, if we have tan inverse of x times square root of x dx, right? Here we have an, not tan inverse of square root of x, tan inverse of x times square root of x dx. Here we have an inverse trigonometric function and any other function. So here we're in guideline 2. So here this thing is your u, and this guy's your dv. And guideline 3 is if we have something like e to the x cosine pi x dx. Right, now here it actually doesn't matter which is your u and which is your dv. They'll both give you the same. They'll both work. They'll both lead to the answer. But here I'm going to call the cos pi x u and the e to the x dx my dv. And the reason is because if you do it in the Liaid order, that's what it says. I might actually do the example I come up with later the other way just to show you it also works. But yeah. But anyways, this is an example of something you can do with guideline 1. Example of something you can do with guideline 2. Example of something you can do with guideline 3. Questions before we move on? Okay. So basically for the rest of the section, I'm going to be going through a bunch of examples, and I'm going to be introducing some new ideas as I go through the examples. So one new idea I'm going to introduce as I go through the examples, this thing is called the KX rule. It's a shortcut for doing integration by substitution. And it's a shortcut for doing integration by substitution in one specific scenario. In the scenario where we have a function of a constant times x. So we have a function, if we have something like e to the 3x, or we have secant squared 5x. Right, those are both things that we can do with substitution. Right, we could do here u equals 3x, du equals 3 dx. So dx is 1 over 3 du, and the end we end up dividing by 3. Here we could do u equals 5x, du is 5 dx. So dx is 1 over 5 du, and we end up dividing by 5. But in general, the rule is this. If the antiderivative of a function on its own is capital F, then if you want to take the antiderivative of a function of k times x, we do the antiderivative, and we divide by k. So if we want to do this guy, we can just say, okay, the antiderivative of e to the x is e to the x, so the antiderivative would be e to the 3x, but then I have to divide by 3. Here, if I want to do this guy, I can think, okay, the antiderivative of secant squared is tangent, so it's going to be tangent of 5x, but then I'm going to have to divide by 5. And again, we could do these with substitution, but there is this shortcut. And this shortcut says that if we have a constant times x, we can always just divide by the constant when we're doing the antiderivative. Sorry, these should have plus c's on them, because they're indefinite integrals. So this rule is going to be useful when doing these integration by parts problems, partly because oftentimes we're going from the dv to the v, we have a situation like this. We don't want to have to do substitution every time to find the antiderivative. We want to be able to just say, okay, we're going to divide by the constant, because that's what the kx rule says to do. If you want to think about it this way, when you're doing, if you took the derivative of this, you have to multiply by 3 because of the chain rule. So in some sense, the kx rule is a shortcut for the antiderivative of the chain rule. But yes.
Is there ever going to be a situation where we have to do substitution first, then integrate the substituted integral?
Yep. That's coming up later. Yep. So there are some situations. Now, if it's something as simple as this, no.
Yeah.
But if it was e to the x squared, x dx. Oh, no, sorry. If it was, here's an example of when you'd have to do substitution first. So, this guy. So the idea here is we can do substitution, right? We can tell you to do substitution because we've got an x squared inside. When we do that, the du is 2x dx. And what's going to happen with the substitution is the x cubed will become half the du. It'll become half, right? So, sorry, du over 2 is x dx, but times another x squared. So here we'll have a u from the x squared part of the x cubed. We'll have an e to the u, and we'll have a du over 2. And because you've got a u, e to the u left, that thing we're going to have to do by parts. But usually you'll be able to tell it's a substitution problem from the beginning because you've got something inside. Yeah. Okay. Any other questions before I do the example using this kx rule? If you didn't understand this one, don't worry about it. I did this really, really quickly to answer Bill's question. I will do one slower later. Okay. So here's an example of one we can do using that kx rule. Here we have example 3, and it's the integral of y e to the 0.2y dy. Now here we have a polynomial function times an exponential function. So we're using guideline 1. And guideline 1 says the u should always be the polynomial function, in this case y, and dv should be the exponential function, which is e to the 0.2y dy. All right, that's what guideline guideline 1 says to do. So then we need to find what du is. Well, the derivative of y is just dy, or the derivative of y is just 1, so du is 1 dy, or just dy. V, now here we have to do the antiderivative of e to the 0.2y. When we're doing that, we're basically doing an integral. Right? We're integrating e to the 0.2y dy. And we could do this by substitution if we wanted to, but to save time, we're transitioning to substitution. We're going to use this kx rule. We're going to think the antiderivative of e to the x is just e to the x. So it's going to be e to the 0.2y, but then we're going to have to divide by the number in front of the x, or the number in front of the y here, which is 0.2. Now another way of writing this is a little bit simpler. Dividing by 0.2 is 1/5. So dividing by 0.2 is the same thing as multiplying by 5. This can also be written as 5 e to the 0.2y. Any questions at this point about how I picked my u or dv, or how I came up with the du and the v here? Again, the v is always the antiderivative of the dv, so it's always the integral of the dv. And again, If we've got like a constant times x, constant times y in this integral, we're going to have to use this thing called the kx rule to do it. And again, don't put any plus c's in at this step. Wait till the end to do any plus c's. Otherwise, it'll get really complicated really fast. Okay. So now we can continue doing the integral. So the rule of integration by parts says we have u times v minus the integral of v du. So we have y times 5 e to the 0.2y, that's u times v, minus the integral of v, which is 5 e to the 0.2y du, which is just dy. Now, this first one I can just write as 5y e to the 0.2y. I'm just changing the order of multiplication. There's nothing wrong with that. This second one, the 5 is a constant. It'll come out front. And then if I want to find the antiderivative of e to the 0.2y, it's going to be the same thing it was up here. It's going to be this. Right? So the first 5 is this 5 here. The second one is the one you get when you do the antiderivative of e to the 0.2y, right? The antiderivative of e to the 0.2y is e to the 0.2y over 0.2, because of that kx rule. And so it's the same thing as 5 e to the 0.2y. And that's what goes in there. You'll notice that if you're doing integration by parts, one of the things that will happen is if there's any constants in your integral, they'll end up coming up multiple times. If you have the same constant twice, like you have 5 times 5. Sometimes you have situations where you have 3 times 3 times 3 times 3 times 3. Just the way integration by parts works. Any questions about example 3? One thing I want to mention about integration by parts is oftentimes we have to do it more than once. Sometimes the first integration by parts results in an integral which is simpler than the one we started with, but is still complicated enough that you need integration by parts to do it. And it's important when doing this that we make sure that the rule we're using to pick the u and the dv the second or the third time around is basically the same as the one we did the first time around. Make sure we pick, like, as close as possible to the same u and dv the second and third time around as we did the first time around. Otherwise, we can end up getting exactly back to where we started. It won't actually get us anywhere. There is a way of doing integration by parts where we pick u and dv one way once. If we switch which is u and which is dv, we'll end up getting exactly the same integral we started with. We won't have actually gone anywhere. We don't want to do that. We want to get to the end of the problem. So here's an example of a problem that's going to need a number of different integrations by parts. Actually, oh great, did I pick a, I'm changing this one. Sorry. I realize this is not exactly, but let me just check what the second one is. Yeah, okay, I'm changing it like this. Sorry, I realize this one, the way it was written, it does not require more than one integration by parts. If I put it as lnp squared, it does require multiple integrations by parts. Sorry, I just realized I need to fudge it a little bit because the way it was written was only going to be one integration by parts. So, so here, again, if we have a logarithmic function or an inverse trigonometric function, that is always my u. So here my u is lnp. And my dv is everything left. It's p to the fifth, oh sorry, lnp squared. And the dv is everything that's left. It's p to the fifth dp. So if I want to find du, I've got to take the derivative of lnp squared. Well, the derivative of lnp squared is going to be 2 lnp times the derivative of lnp. The derivative of lnp is 1 over p. And my v is going to be the antiderivative of p to the fifth, which is p to the 6 over 6. So this integral will become the integral of, oh sorry, will become u times v. U times v here is going to be ln p squared times p to the 6 over 6 minus the integral of v du. So v here is p to the 6 over 6. Du is 2 ln p times 1 over p. Now this one looks really complicated, but if we simplify it, it will get simple enough that we can move on. So, figure out where I can stand that I don't block the board too much. I think if I stand here, I can, people over there can read, everyone can read that side. Okay, so the first part, ln p squared times p to the 6 over 6, you can't really do much with that. The second part, though, here, you'll notice there's a p to the 6 on top, there's a 1 over p. That'll cancel to give you a p to the 5th. You have a 2 on the top and a 6 on the bottom. That'll turn into basically a 3 on the bottom. And otherwise, you just have an ln p. And this 3 here, you can actually bring out front as a 1/3. So we can write this as 1/3 integral of p to the 5th ln p dp. So you'll notice that that is simpler than the one we started with. You know, it's almost the same, right? Still got a p to the 5th, but the only difference is rather than an ln p squared, it now just has an ln p. So it is simpler, and we always want to pick the u and the dv in the same way as we did the first time around. So in this case, the u is going to be the ln p, and the dv is, of course, the same thing as it was in the beginning, is p to the 5th dp. So again, almost the same as the u and the dv we started with. Here, if u is ln p, du is going to be the derivative of ln p, which is 1 over p. And then you have to write dp next to it, because that's what you do when you do a d of something, you always have to write the dx type part. And dv is p to the 5th. V is the antiderivative of p to the 5th, which is p to the 6 over 6. So now we can do integration by parts again. This thing at the beginning is still going to be there. We're still going to have ln p squared p to the 6 over 6. But the second part here will change. The second part here will become a uv minus v du. Now notice I put this 1/3 here in front of an open bracket. And the reason for this is because it's this whole integral, which I'm replacing with uv minus v du, and the 1/3 is multiplied by the whole integral. So uv here is ln p times p to the 6 over 6 minus the integral of v, which is p to the 6 over 6, du, which is 1 over p dp. So here we'll have ln p squared p to the 6 over 6 minus. Now if we simplify this, well, I'm actually not going to simplify it too much. That first thing I'm just going to leave as ln p times p to the 6 over 6. Just going to leave it as it is. This guy will simplify. P to the 6 on the top and p on the bottom will cancel to be a p to the 5th. And the 1/6 can come out as a constant. So we'll get something like that, 1/6 times integral of p to the 5th dp. And then last but not least, we could actually evaluate this integral. Integral of p to the 5th is, p to the 6 over 6. So we have 1/6 times p to the 6 over 6. Everything at the beginning is going to be the same. So we'll still have ln p squared p to the 6 over 6 minus 1/3, open bracket, ln p to the 6 over 6 minus this thing. And again, at the very end, that's when you tack on the plus c. Don't add the plus c until the very last step, because otherwise there's nothing wrong with doing it before, it just makes for a more complicated solution. So this is the final answer for example 4. And we're doing example 4, and we'll just do integration by parts twice. Once here, and wants to evaluate this integral that we got from doing it the first time around. Any questions before we move on? Okay, example 5. Here's another one where we're going to have to do integration by parts more than once. So here, now here I also have a depth integral. Here we have integral from 0 to 1, x squared plus 1, e to the negative x dx. So here we have a polynomial function times an exponential function. In that case, we always call the polynomial function u, and the exponential function is going to be your dv. That's that first guideline for how we pick what's u and what's dv. If u is x squared plus 1, du is 2x dx. Right, the root of x squared plus 1 is 2x, put the dx on there. If dv is this, v is e to the negative x over negative 1. Here again, I'm using that kx rule. It's not just e to the x, it's e to the negative 1 times x. So it's the number times x, you have to divide by that number here. So we're going to write out the new integral. So we're going to have u times v to start off with. So x squared plus 1 times e to the negative x over negative 1. This whole thing goes from 0 to 1. Because you always have to put on those limits of integration when we're doing definite integrals. Minus the integral of v, which here is e to the negative x over negative 1 du, which is 2x dx. And again, same limits of integration are going to be there, from 0 to 1. I'm going to need more space to continue this, so I'm going to switch over to the board over here. So, we're going to plug in those limits of integration into the first thing. So 1 squared plus 1 times e to the negative 1 over negative 1 minus 0 squared plus 1 e to the 0 over negative 1. Now for the second one, I'm going to simplify it. I can pull a 2 out front. I can pull this negative 1 out front. The negative sign will cancel the negative 1. So I will get plus 2 integral from 0 to 1 x e to the negative x dx. So I'm just going to mention this first thing will simplify. 1 squared plus 1 is 2. Divided by negative 1 gives you negative 2. Here I have negative 2 e to the negative 1. Here, these negatives will cancel. E to the 0 is 1, so plus 1. That's what this whole first thing will simplify to. Again, if you don't want to do that simplification stuff, I'm not going to take off marks on your final answers on the tests. It's just nice to do because it saves space on the page for the rest of the steps. Then I've got to do another integration by parts for this one. I still have a polynomial function times an exponential function. So my u is going to be x. My dv is going to be e to the negative x dx. My du is going to be the derivative of x, which is 1. My v is going to be the antiderivative of this, which is e to the negative x over negative 1. So here I'm going to have 2 times u times v is x e to the negative x over negative 1 minus, this thing's got to go from 0 to 1, put in the limits of integration, minus the integral from 0 to 1 of v du, e to the negative x over negative 1. Oh, 1, sorry. There should be a dx here. dx. I'm just going to rewrite this part so it's more clear. E to the negative x over negative 1. There we go. So we're going to evaluate this whole thing. We have negative 2 e to the negative 1 plus 1 plus here. We plug in 1. We have 1 e to the negative 1 over negative 1. Plug in 0. We have 0 e to the 0 over negative 1 minus negative 1, negative 1. Those will cancel, give you a positive. Integral from 0 to 1 e to the negative x dx. This part's just going to stay, negative 2 e to the negative 1 plus 1 plus 2. This will just be negative e to the negative 1. Here, if we want to integrate e to the negative x, we've got to use that kx rule again. It's going to be e to the negative x over negative 1. And we've got to put in those limits of integration, 0 and 1. The final answer, there'll be a negative 2 e to the negative 1 plus 1 plus 2 times. This part's going to stay the same, negative e to the negative 1. This part, I'm going to put in 1. I'll have e to the negative 1 over negative 1 minus, I put in 0. E to the 0 over negative 1. I close those brackets, and that's the final answer. Again, integration by products problems can end up with annoyingly long answers in the end. Definitely, if I give you an integration by parts problem on a test, we have to do it more than once, or on the quiz that's next week, I'm going to make sure you've got lots of time to do it and lots of space on the page to do it. Any questions about this example 5 here? Yes?
If we struggle with like actually picking the proper U and D's and stuff,
Yeah.
how would it work with part marks on a test?
That's a good question. So if you, okay, so usually, for example, in this problem, this is a good example, there'll be 1 mark for picking the right U and dv, 1 mark for doing the first integration by parts step, another mark for picking the second U dv, another mark for doing the second integration by parts steps, and maybe 2 or 3 marks from what happens from there on. So the idea is if you pick the wrong U and dv, you'll lose this mark, but if you do the integration by parts correctly, you'll get a mark for doing that.
Okay.
So you will, now if you try a second U and d, and if you pick the right U and dv for the whatever new integral you get, you'll get that mark too.
Oh, nice.
So that, I was going to say, now if you, so I was going to say, you will get marks for doing correct procedures, even if they're going in the wrong direction.
Okay.
Yeah. Now I was going to say, oftentimes if they don't take you in the right direction, you will lose these marks at the end for actually simplifying your final, or not simplifying, for evaluating this final integral that you can evaluate. But you will get the marks for, if you show me that you can do integration by parts correctly, you will get marks for that. Yeah. Yeah. And same thing with substitution. If you choose the wrong substitution, but you do the substitution correctly, you'll get marks for doing the substitution correctly. Although if you do the wrong substitution, you won't actually get anything that you can actually evaluate. Yeah. Any other questions about example 5 here? Okay. So this next slide I call integrating in circles. This sort of weird situation that I mentioned before, which happens when you've got a trigonometric function times an exponential function, or specifically a sinusoidal function, like sin x or cos x times an exponential function. You can do it with like tan x times an exponential function. I am not going, but it's a lot harder. I'm not going to make you do that in this course. So just the only ones you'd have to worry about is sin x or cos x times an exponential function. And what will happen when you do this is you'll do integration by parts twice, and after you've done integration by parts twice, you'll notice you get the same integral that you started with. You'll think, oh darn it, I've gone in circles. But you actually haven't quite gone in circles, because you will get the same integral you started with, except there will be a constant in front of it. And that constant that's in front of that integral is key. Because what you can do is you can actually take that integral and you can actually move it to the other side of the equation. When you move it to the other side of the equation, it'll become a lot nicer and it'll become something you can actually solve for that integral. Usually to do this, I call that whole integral I. I give it a name because it's easier to solve the equation for I. So here's the example I want to do, e to the negative theta cosine theta d theta. Example 6. So here, for argument's sake, I'm going to pick my u to be cosine theta, my dv to be e to the negative theta d theta. Then my du, the derivative of cosine theta, is negative sine theta. My v is e to the negative theta over negative 1. So my new integral is going to be u times v. So this whole thing equals cosine theta times e to the negative theta over negative 1 minus the integral of v, which is e to the negative theta over negative 1 du, which is negative sine theta. Oh, sorry, d theta. Right, so that's what happens when you do integration by parts once. Again, if you want to pick your u to be this and your dv to be this, you'd get the same answer in the end. So don't worry too much about what you want to pick to be your u, what you want to pick to be your dv. This first thing I can simplify to negative cosine theta e to the negative theta minus, oh sorry, these two negative signs cancel, but this negative sign will give you a new negative sign, right? So you've got 1, 2, 3 negative signs, and 3 negatives make a negative. So it's going to still be negative, and we're just going to have e to the negative theta sine theta d theta. So to keep going, we're going to need to go do integration by parts again. Here, I'm going to pick my u and dv to be as similar as possible to the original ones. So here I'm going to pick my u to be sine theta and the dv to be e to the negative theta d theta. Again, they can't be exactly the same because there's no cos theta here, but there is a sine theta here. My du, the derivative of sine theta, is cos theta. And again, you have to tack on that d theta. The v is the antiderivative of e to the negative theta, which is e to the negative theta over negative 1. So, as we continue, we will get negative cosine theta e to the negative theta minus, open bracket, here we're going to put u times v, which is sine theta e to the negative theta over negative 1, minus integral of v e to the negative theta over negative 1 du. Sorry, I'm going to make this smaller so I can fit it all in. Negative cosine theta e to the negative theta minus, minus bracket, e to the negative theta over negative 1 sine theta minus integral e to the negative theta over negative 1 cosine theta d theta. So as I simplify this, there's a couple things I'm going to do. I am going to distribute this negative sign. So this guy and this guy will cancel, basically. And I'll have a plus e to the negative theta sine theta. This negative sign and this negative sign will also cancel, but this one here will add another negative sign. So minus integral of e to the negative theta cosine theta d theta. So now what I have is an equation which says that, you'll notice, sorry, this is the same integral that we started with. Right? I said we've gone in circles here. But we haven't quite gone in circles here because now it has a negative sign in front of it. And it didn't have a negative sign in front before. So you've actually gotten something slightly different from what we started with. What we've gotten is that this integral equals this thing plus this thing minus the same integral. So if we call this integral I, we've got an equation which says that I, that integral, equals negative cosine theta e to the theta plus e to the negative theta sine theta minus I. And this is an equation we can solve for I. All we need to do is take this negative I and move it to the other side. Now a negative I moved to the other side will become a positive I. So we'll get 2I equals negative cosine theta e to the theta. Oh, this was a negative theta. Negative theta, negative theta, e to the negative theta sine theta. We want to solve, so we're going to have 2I equals this. Divide both sides by 2. So I equals negative cosine theta e to the negative theta plus e to the negative theta sine theta all over 2. And that is what the integral gives you. Oh, plus c. And again, this is one of these things, if integration by parts problems, don't add the plus c until the final step. So the idea is if you do integration by parts twice, you get an integral that's the same as the original one you started with. What you can actually do is call this thing you started with I, and because there's going to be a number in front of this I here, when you move it over to the other side, you'll get a number times I on the other side. Divide by that number, and we've got a solution. The integral is this. It's a sort of, it seems like it's cheating sometimes to like say, okay, well this thing is I moved to the other side, but it works, and it will give you the correct answer. If you actually take the derivative of this, you will get this guy. It'll be a lot of work to do that, so I'm not going to do it, but, okay. So I'm going to give you the break at this point, because I've realized I'm about 10 minutes behind where I wanted to be. That's okay. So take 10 minutes. We'll start again at 1:45. Oh, no, sorry. Got to hand back the tests first. I'm going to hand back the tests, and then we will start again at probably 10 minutes to 1. This one's 1. Okay. So Joshua. There you go. Amanda. Marlo. Oh, there you are. Who's right there? Abby, Sunny, Ellen, Harleen, Daryl, Michelle, Kyle, Brian, Justin, Jackson, Mike, Brandon, there you are. Dylan is usually not here today. Danielle, Alicia, yeah, and then Katerina, Kate, Sam, Mandy, Integrate, Dave, Harman, Ryan, Joel, Dmitri. Is there anyone here who get theirs? Good. Just wanted to make sure. Okay. If you have any questions about it, please let me know.